If you've ever wondered why baby skin feels like rose petals while elderly skin feels more like parchment paper that's been through a desert hike, the answer lies not just in sun damage or collagen loss, but in the strange evolution of a single, quiet cell type, the fibroblast. These unsung heroes of the dermis are responsible for making the scaffolding that keeps skin plump, elastic, and hydrated. But as we age, fibroblasts don't just get tired. They change personalities entirely, some going rogue in ways that would make a villain origin story proud. Now, thanks to single-cell spatial transcriptomics and machine learning, researchers are building a comprehensive 3D atlas of fibroblast senescence, giving us the first real glimpse of how these cells morph and misbehave across the human lifespan. Imagine being able to scroll through a time-lapse movie of your skin at the cellular level, from the bouncy fibroblasts of a 5-year-old to the cranky, SESB-spewing cells of an 85-year-old. That's essentially what this new atlas aims to achieve. It uses high-resolution spatial transcriptomics, a technology that lets scientists measure gene expression in individual cells while preserving their exact position in tissue, to map where fibroblasts are located, what they're doing, and how that changes decade by decade. Overlay that with machine learning algorithms trained to recognize senescence markers like CDKN2A, P16, CDKN1A, P21, and SESB components, and you get a living, breathing, okay, not literally, model of skin aging. What's emerging from this 3D atlas is a story that's much more nuanced and weirder than anyone expected. In young skin, fibroblasts are like a well-rehearsed orchestra. Papillary fibroblasts near the epidermis produce tight bundles of collagen. Reticular fibroblasts deeper down manage structural integrity, and a third set of progenitor fibroblasts hang back in reserve. Most of them are dividing, responsive, and relatively quiet on the inflammatory front. But by middle age, the concert starts to go off-key. Spatial transcriptomics reveals a creeping spread of senescent subtypes, especially in sun-exposed areas like the face and hands. Some fibroblasts begin secreting MMPs that chew up collagen, while others start producing cytokines like IL-6 and IL-8, contributing to chronic low-grade inflammation, aka inflammaging. These SASB-positive fibroblasts aren't evenly distributed. They cluster in microniches, often near hair follicles or blood vessels, where they create local zones of chaos. Think little skin cul-de-sacs where aging throws a block party and refuses to leave. By old age, the situation gets even stranger. Fibroblast diversity declines, not because there are fewer cells, but because the population becomes dominated by senescent subtypes with rigid gene expression profiles. The progenitor pool dwindles, regenerative capacity flatlines, and many fibroblasts shift into a persistent pro-inflammatory, matrix-degrading state. It's not just that the cells are old, they're loud, cranky, and biologically influential in all the wrong ways. Even worse, they seem to train neighboring cells to adopt similar dysfunctional states via paracrine signaling, like grumpy seniors shouting inflammatory conspiracies across a cellular bingo hall. The atlas also shows regional variation. Facial skin fibroblasts tend to senesce earlier and more aggressively, likely due to UV exposure and thinner dermal structure. In contrast, protected areas like the inner arm age more gracefully, with a higher proportion of functional fibroblasts persisting well into late life. This spatial data could explain why some parts of the body stay smoother or heal better than others, and why anti-aging creams that work on your cheek might flop on your neck. So what does this all mean for therapy? A lot, actually. If we can identify the exact fibroblast subtypes responsible for visible aging and tissue dysfunction, and map where they accumulate, we can design targeted interventions. Think subtype-specific senolytics, precision skincare that targets specific zones, or even rejuvenation strategies that restore fibroblast diversity and balance. There's even potential for early diagnostics. If your fibroblast atlas looks 20 years older than your chronological age, that might signal accelerated biological aging or underlying disease risk. And let's not forget the aesthetic appeal. Instead of chasing vague claims about plumping or anti-wrinkle peptides, future skincare could come with a printout of your personal skin senescence map and a treatment plan based on actual molecular data. It sounds absurd now, but so did genome sequencing in the 1990s, and today, you can get yours done faster than a mani-pedi. Ultimately, this fibroblast atlas is more than just a scientific tool. It's a time machine made of cells, a map of how we wear the years on our skin, and a blueprint for how we might rewrite some of those years, selectively, precisely, and with a lot more style than a generic retinol cream. Because aging might be inevitable, but aging without a map? That's just bad planning.